Let's plunge to understand in detail the concept of electric field, flux, Gauss's law, and to solve some numerical problems based on these. We have seen that as we place a test charge capital Q in the vicinity of a source charge small q, the test charge begin to feel a force which is given by F equal to Q times E. From this definition, the electric field E can be written as E equal to F over Q. And we define the electric field as the force that a unit positive charge experiences when placed in the vicinity of a source charge. And this definition of the electric field gives two important characteristics of the electric field. First one, electric field E is a vector quantity with magnitude directly proportional to the force and with a direction given by the direction of force on a positive test charge. And E has units of newtons per coulomb, which are the same as volts per meter, since volts equal to Newton times meter over coulombs. Now, for a point charge, the electric field is given by ER equal to 1 over 4 pi epsilon 0 Q over R square times R hat, where R hat is the direction of the electric field. Now we see that the field falls off like 1 by R square, and a representation of this field would be like this. That is, the vectors get shorter as we go away from the center. And every such line of force originate from a positive charge and end on a negative charge. And the tangent to the line of force at any point gives the direction of E at that point. In the case of two like charges, the lines of forces repel each other. These lines of forces never intersect. If it happens, then we say that at the point of intersection, the electric intensity is zero. Otherwise, the direction of the field has to be tangential to two different curves at the same instant, which is impossible. The relation between the electric field and its sources can be expressed in a remarkably simpler way by defining a new quantity called the flux. Let us consider some electric field in space and an arbitrary closed surface like a balloon as shown in this figure. Now, divide the whole surface into little patches that are so small that over any one patch, the surface is practically flat and the vector field does not change appreciably from one part of the patch to another. The area of the patch has a certain magnitude in square meters. Also, the patch has an outward pointing normal n hat to its surface as shown. The elemental area vector can be defined as dA equal to dA times n hat, where dA is the area of an elemental patch. If EI is the electric field vector at the location of patch number I, the scalar product EI dot dAI is a number. We call this number the flux through that bit of section. To understand the origin of the name, imagine a vector function that represents the velocity of motion in a fluid, say a river. The arrows that you see indicate the velocity of motion. The velocity varies from one point to another, but is constant in time at any one position. Let us denote this vector by v. Let us assume that we have lowered a frame into this water, and this frame has an area dA. And when we take the dot product v dot dA, this will actually give the rate of flow of water. So v dot dA is the rate of flow of water through the frame in cubic meters per second. In the first case, the frame is perpendicular to the direction of flow. In this case, the rate of flow will be finite. Whereas in the second case, the frame is parallel to the direction of flow. In this case, the rate of flow will be equal to 0 since v dot dA is equal to 0. If the frame is inclined at an angle theta, then the cos theta factor in the standard expression for the dot product correctly picks out the component of v along the direction of dA, or equivalently, the component of dA along the direction of v. And this definition of flux is applicable to any vector function, whatever physical variable it may represent. When we add up the flux through all the patches, we will get the flux through the entire surface. We will denote this by phi, and this is given by sum over I EI dAI. This is the dot product of vector EI and the elemental area dAI. If we let the patches become smaller and smaller with a larger number of patches, we pass the sum into a surface integral. So in that case, phi will be equal to integral E dot dA. Gauss's law is an important theorem in electrostatics. To understand Gauss's theorem, let us consider an isolated point charge Q and an imaginary sphere of radius R centered on the point charge. Now the flux of E is given by phi equal to integral E dot dA, and this is equal to closed integral 1 over 4 pi epsilon 0 Q over R square times R hat. And then the area element can be written as, this is dotted with the area element, that is R square sine theta d theta d phi R hat. This is equal to Q over 4 pi epsilon 0 closed integral sine theta d theta d phi. So this is equal to Q over 4 pi epsilon 0 integral sine theta d theta integral d phi. The limit of sine theta is from 0 to pi, and that of phi is from 0 to 2 pi. So this integral yields Q over 4 pi epsilon 0. When we integrate d phi, we'll get 2 pi, and when we integrate integral sine theta d theta, we'll get negative cos theta from the limits 0 to pi. So this is equal to negative of Q by 2 epsilon 0 negative 1, and which is equal to Q over epsilon 0. That is, the total flux piercing the sphere is a constant. This means that if we change the radius of the sphere, that is not going to affect the flux that is piercing. In fact, the surface need not be a sphere. Any closed surface, whatever be its shape, would be pierced by the same number of field lines. Evidently, the flux through any surface enclosing the charge is q over epsilon 0. Instead of a single charge, if we have a bunch of charges at the origin, according to the principle of superposition, the total field is given by E equal to sum over I equal to 1 to n EI. The flux through a surface that encloses them all is given by integral E dot dA. So this is equal to sum over I equal to 1 to n contour integral EI dot dAi. And this is equal to sum over I equal to 1 to n Qi over epsilon 0. And for any closed surface, this will be equal to Q enclosed divided by epsilon 0, where Q enclosed is the total charge that is enclosed within the surface. And this is the quantitative statement of Gauss's law in the integral representation. The integral equation of Gauss's law can easily be turned into a differential equation by applying the divergence theorem. According to divergence theorem, if we have a closed contour integral E dot dA, this will be equal to a volume integral del dot E d2. And this is equal to Q enclosed over epsilon 0. When we rewrite Q enclosed in terms of the charge density rho, we have this equation as equal to integral V rho d2 over epsilon 0. And hence the Gauss's law becomes volume integral del dot E d2 equal to volume integral rho over epsilon 0 times d2. And since this holds for any volume, the integrand must be equal. That means del dot E equal to rho over epsilon 0. This is the Gauss's law in differential form. Now let us try to solve problem number 5. The electric field in some region is found to be E equal to k r cube times r hat in spherical coordinates. Here k is some constant. Part A of the problem is to find out the charge density rho. According to Gauss's law, we have del dot E equal to rho over epsilon 0. And hence, we have rho as equal to epsilon times del dot E. This is epsilon 0 times 1 by r square dou over dou r of r square k r cube in spherical coordinates. So this is equal to epsilon 0 1 over r square k times 5 r raised to 4. And this is equal to 5 epsilon 0 k r square. Part B of the problem is to find the total charge contained in a sphere of radius r centered at the origin. And this can be solved by two methods. The first method is by employing Gauss's law. According to Gauss's law, we have Q enclosed is equal to epsilon 0 times closed integral E dot dA. And this is equal to epsilon 0 integral K R cube R hat dot R square sine theta d theta d phi then R hat. So this is equal to epsilon 0 times K integral R raised to 5 sine theta d theta d phi. So this is equal to epsilon 0 K R raised to 5 integral 0 to pi sine theta d theta then integral 0 to 2 pi d phi. So this is equal to epsilon 0 K R raised to 5 times 2 pi times negative of cos theta from 0 to pi, or Q enclosed is equal to epsilon 0 K R raised to 5 times 2 pi times negative of negative 1 minus 1, which is equal to 4 pi epsilon 0 K R raised to 5. We can also solve this problem by direct integration. In that case, we have Q enclosed is given by rho times d tau. And this is equal to integral 0 to r 5 epsilon 0 K R square, which we have found out from the first part of this problem, and then d tau is given by 4 pi R square dr. And this is equal to 5 epsilon 0 times K times 4 pi times integral 0 to r raised to 4 dr, which is equal to 20 pi epsilon 0 K then r raised to 5 over 5 within the limits 0 to r. And when we apply the limits, we'll get 4 pi epsilon 0 K times r raised to 5. Let us now try to calculate the divergence of E from the integral equation involving the charge density rho. Remember, the enclosed charge Q enclosed and the charge density rho are related as integral rho times d tau. Now, when we take the divergence, that is del dot E, this is equal to 1 over 4 pi epsilon 0 integral del dot r hat over r square rho vector r prime d tau prime. Now recollect this equation involving the Dirac delta function. Del dot r hat over r square equal to 4 pi del cube vector r. Thus, del dot E becomes 1 over 4 pi epsilon 0 integral 4 pi del cube vector r minus r prime rho r prime d tau prime. And this will be equal to 1 over epsilon 0 times rho r. And this is the Gauss's law in differential form. If we want to recover the integral form, we can use the divergence theorem. That is volume integral del dot E d tau equal to surface integral E dot dA. And this is equal to 1 over epsilon 0 integral rho d tau, and that is equal to Q enclosed over epsilon 0. When there is a symmetry in the problem, the integral form of Gauss's law can be used to calculate electric fields in a simpler way. And there are three kinds of symmetry that work. The first one is a spherical symmetry. In this case, the imaginary Gaussian surface will be a concentric sphere. If the problem has some kind of a spherical symmetry, the Gaussian surface will be a coaxial cylinder. And if there is plane symmetry, the Gaussian pillbox that straddle the surface will help us to solve any complicated problem in electrostatics. We'll now try to solve this problem. Find the field outside a uniformly charged solid sphere of radius r and total charge q. To solve this problem, we need to have an imaginary Gaussian surface. So let us assume that this one is a Gaussian surface, which is spherical in shape. The radius of the sphere is given by capital R and that of the imaginary Gaussian surface as small r. Then according to Gauss's law, we have the surface integral E dot dA as equal to 1 over epsilon 0 Q enclosed. In this case, we are given that the enclosed charge is Q, and therefore this equation becomes Q over epsilon 0. An important point with regard to this surface is that E and dA point outward. And since they point outward, we have E dot dA as equal to E, which is directed along the R direction, dot dA, which is directed along the R direction. And when we take the dot product, this will be magnitude of E times magnitude of dA. Therefore, when we take the surface integral E dot dA, this will be equal to surface integral E dA. This is equal to E times integral 0 to 2 pi integral 0 to pi r square sine theta d theta d phi. And as before, this integration becomes E times 4 pi r square. That is E times 4 pi r square is equal to Q over epsilon 0. From this, we'll get the electric field as 1 over 4 pi epsilon 0 Q over r square times r hat. This equation resembles the field that is generated by a point charge Q. Now, from this we understand that the field outside the sphere is exactly the same as it would have been if all the charges were concentrated at the center. Now, problem 7 is to use Gauss's law to find the electric field inside and outside a spherical shell of radius capital R that carries a uniform surface charge density d sigma. Now the relationship between dq and d sigma, if you remember, is given by dq equal to sigma times dA prime. Now let's try to find out the electric field inside this spherical shell. We have Gauss's law given by closed integral E dot dA equal to Q enclosed over epsilon 0. Since E is everywhere normal to the Gaussian surface, as before, we have E dot dA equal to E times r hat dot dA times r hat, and this is equal to E dA. Therefore, when we calculate E dot dA, this will be equal to closed integral E dA, and this is equal to E times integral 0 to 2 pi integral 0 to pi r square sine theta d theta d phi, and this is equal to E times 4 pi r square, which is again equal to Q enclosed over epsilon 0. But the charges are actually on the surface of the sphere. Let us assume that these are all positive charges for the time being, and these charges are all on the surface of the sphere. Our imaginary Gaussian surface is actually inside the sphere. And this imaginary Gaussian surface does not enclose any charges, and therefore this is equal to 0. That means that the electric field inside the spherical shell is 0. Outside the spherical shell, E times 4 pi r square will be equal to 1 over epsilon 0. Then from the very definition of sigma, we have sigma times 4 pi r square. That is E as equal to sigma r square over epsilon 0 r square. When expressed as vector, E will be equal to sigma r square over epsilon 0 r square times r hat. In problem number 8, we have to use Gauss's law to find the electric field inside a uniformly charged solid sphere having charge density rho. Remember, dq and rho are related as dq equal to rho times d2. Now, according to Gauss's law, we have integral E dot dA as equal to E times 4 pi r square, which is equal to 1 over epsilon 0 Q enclosed. So in this case, the imaginary Gaussian surface is inside the sphere, and this is the distance r, and this is equal to 1 over epsilon 0 rho times 4 by 3 pi r cube, where r is the radius of the Gaussian surface. And this equation gives us E as equal to 1 over 3 epsilon 0 rho times r. Or vectorially, E is equal to 1 over 3 epsilon 0 rho r times r hat. Let's now try to rewrite this equation in terms of the total charge Q total. The total charge on the solid sphere is related to the charge density as 4 over 3 pi r cube times rho. Therefore, the electric field is given by 1 over 3 epsilon 0 Q total divided by 4 by 3 pi r cube times r hat, and this is equal to 1 over 4 pi epsilon 0 q over r cube times r hat, and this is the expression for the electric field inside a uniformly charged solid sphere having charge density rho. Problem 9. Find the electric field a distance s from an infinitely long straight wire that carries a uniform line charge. Let us consider a uniform wire. And in this case, the symmetry allows us to use a cylinder as the imaginary Gaussian surface. We are asked to find out the electric field at a distance s from the infinitely long straight wire. And let us also assume that L is the length of this cylinder. Now, from Gauss's law, we have closed integral E dot dA as equal to E times 4 pi r square, and that is equal to Q enclosed over epsilon 0. In terms of the line charge lambda, we can write Q enclosed as lambda times L. And from this, we have the electric field as given by lambda over 2 pi epsilon 0 s directed along the direction s hat. Here r is equal to s. Problem 10. An infinite plane carries a uniform surface charge sigma. Find its electric field. So what you see in gray color is an infinite plane, and this carries a surface charge sigma. We have to find out the total electric field that is generated by this infinite plane. So the symmetry of the problem allows us to use something known as a Gaussian pillbox. So this is the Gaussian pillbox, and A represents the area of the face. We assume a pillbox enclosing the infinite plane surface. The Gaussian pillbox extends equal distances above and below the plane. When we apply Gauss's law to this surface, we have E dot dA as equal to 1 over epsilon 0 Q enclosed. So this is equal to 1 over epsilon 0 sigma times A, where sigma is the surface charge density and A is the area of the lid of the pillbox, that is this area. By symmetry, E points away from the plane. If you are considering a point above the surface, then E points in this direction. And if you are considering a point below the infinite plane, then E points towards this direction. And hence, the top and bottom surfaces of the plane yield integral E dot dA as equal to E dA, which is equal to 2 times EA. And the sides of the Gaussian pillbox, that is these sides, will contribute nothing. Thus, we have 2A E equal to 1 over epsilon 0 sigma times A, or E equal to sigma by 2 epsilon 0 n hat, where n hat is a unit vector pointing away from the surface. Problem 11 is an extension of problem 10. In this case, we have two infinite parallel planes that carry equal but opposite uniform charge densities plus or minus sigma. So there are two planes, and this plane, the first plane, carries a surface charge density plus sigma, and the second one carries a surface charge density minus sigma. Find the field in each of the three regions. Region 1, so this is region 1, which is to the left of both, and region 2 is that between these two parallel planes, and region 3 is right to both of these planes. We have to find out the electric field in each of these three regions. In the previous problem, we have seen that the total field produced by a plane is sigma over 2 epsilon 0. Now, let us analyze these planes individually. So, this is the first plane having surface charge density plus sigma. This plate produces a field E equal to sigma over 2 epsilon 0, which points away from it. That is, to the left in region 1 and to the right in regions 2 and 3. Now the right plate is negatively charged, and this produces a field sigma over 2 epsilon 0, which points towards it in regions 2 and region 1 and to the left in region 3. And the fields in region 1 and that in region 3 cancel each other because they are equal and opposite. The only field that remains is the field between the plates, that is directed to the right. And the total field will be E equal to E plus plus E minus, and this is equal to sigma over 2 epsilon 0 plus sigma over 2 epsilon 0, and that is equal to sigma divided by epsilon. Remember, E is modulus of E, and E plus is modulus of E plus, and E minus is modulus of E minus. And this field will point towards the right, and everywhere else its value is 0.